Okay, I think everyone is already in the room, so I think we can start. So, hello everyone. My name is Mateusz Kubuszok. I will be showing you my presentation about semi-automatic and automatic derivation from the user's perspective. So don't worry, I will not show you any sort of macros, shapeless, magnolia, mirrors, things like that. I will only tell about how authors picking up which tools they use to design the library affects you as the users. And also mentioning a little bit how other libraries, like some libraries do this and how it affects you. So probably most of you are used to using some libraries which are based on type classes. Maybe you're not aware of that, maybe you are, but basically it's really hard to have a Scala code base which isn't based on some sort of type class derivation and type classes and all of that stuff. Perhaps some of you who are used to those kind of libraries notice that sometimes you are able to use something called automatic derivation. Sometimes you have to manually tinker with things with this thing called semi-automatic derivation. Sometimes you suffer due to long compilation times or really bad compilation method errors, which tells you nothing. So in this presentation, we will try to talk a little bit how all those different choices, not made by you, but by the basically libraries developers, affect you as a user, and if there is something if we could, do better and expect more of all those libraries. So a little bit about me. I've been working with Scala for over 9 years. I gathered some experience, jumped between many different projects. So about as much of all those weird stuff as many of you in this room have seen. In the meantime, I was also doing a little bit of open source. I think the biggest stuff I co-authored was the Chimney library, which I am co-maintaining for over 7 years now. Maybe some of you heard about this library. It's one of the reasons, it's the stuff that is written here as the stuff I am developing. However, I will not show you any sort of Chimney stuff on this presentation. I was also blogging a little bit, and at some point I also wrote this niche book when I tried to explain how Scala is working on JVM, how we can debug that, how we can understand what is Scala actually doing on the JVM, how it impacts us. Sometimes it gets useful. But enough about me, let's talk about today's topic. So the plan for this presentation is as follows. At first we will start by reminding what is a type class, because even if most of you and most of the people out there were using type classes in this way or the other, maybe not everyone is aware what it is and how they were using it, and maybe someone is just learning Scala and seeing all of the stuff and not necessarily understand what this stuff is about. Then we will also speak a little bit about what is this type class derivation, because basically it's the topic of this presentation, and if someone came in this room, straight from the university, never working with Scala, they might be thinking that perhaps derivation have something to do with integrals and calculus, and no, it doesn't. It's just the same name, so it would be good to mention what it is about. Then we will talk a little bit about these things called automatic and semi-automatic derivation, because for some reason in Scala we decided to use two flavors of the derivation are needed. So perhaps it's worth knowing why they are needed, or are they actually needed. Then we could take a look at, and this first example will be based on Circe, and I am calling it this derivation a la Circe because This library really propagated this pattern of automatic and semi-automatic derivation, whatever it is. We'll talk about it later. However, not all the libraries out there are following it, and as an example of that, we'll take a look at JSON-eater and how it affects you as a user when you use it. And finally, I want to tell a bit about something I call sanely-automatic derivation, and I'm calling it sanely because after years of working with derivation and all those libraries, I started to thinking that this automatic versus semi-automatic derivation is kind of insane, especially if you want to be user-friendly and beginner-friendly and explain to people how they can use stuff in as simple manner as in Java, as opposed to doing all this weird stuff that you sometimes have to do when you are working with the way we got used to doing. And obviously, as I said before, I want to talk from the user's perspective. So I won't be doing any sort of Magnolia tutorial, Shapeless tutorial, Mirrors tutorial, and I will not show you any of such code. Even though this code, whether or not it's used and how it's used, will be affecting some of the results that will be shown here today. But if some of you are being curious about how I got the results that I'm willing to present to you and rerun the benchmarks and then see where I got wrong and how I don't understand how to use Shapeless properly and how I don't understand how to benchmark JVM properly, you can always take a look at this repository when I'm storing all of the code that was used to generate the results that I will be showing you today. I will show this QR code also at the end of the presentation, so don't worry if you will not be able to catch it right now. I will be showing it also later. So let's start. What is a type class? As far as I care, it's first of all an interface. But it's not any interface, it's an interface which has some type parameters. That is really important. If you have interface with no type parameters, you cannot really call it a type class because implementation of this interface will be provided by the compiler to you based on the type solely. So if you have an interface with no type parameters, well, compiler can only know that there is one implementation it can provide to you through this magical mechanism called implicits. So if you want to have a variety of interfaces with a variety of implementations, they have to be distinguishable by some of these type parameters, actually only by those type parameters. So maybe some example to understand what do we mean by that. Let's say we want to have an encoder. Example from the CRC library, obviously. So we have some type. Maybe it's a case class, maybe it's a sealed trait, maybe it's an enum, maybe it's some primitive, whatever. And we want to turn it into JSON. And we have, let's assume that we have this JSON, which is JSON represent as some data which we could render as actual string or whatever. And this is the interface. And then we are using this implicit or givens, as they are called in Scala 3, as this mechanism of providing those implementations. So we could provide an implementation for string, for int, for double, for example. Then we can use, let's say, extension method because we want to be very convenient to get that implementation by its type and use it. First, as this way. We have a string, we call this extension method xString. As a string, Scala will figure out, okay, I need to have the implementation of the encoder, which is implemented for strings, so let's see if we have some given for it. It's fine, okay, let's use it. Same for ints, doubles. It's simpler than it sounds. You just have to get used to it, experimenting with the code, and it will click, believe me. What not always will click is, what if there is no implementation for your type? Nobody wrote it, nobody provided it. You have your type, you define it, and nobody wrote special implementation just for it. And you try to use this extension method. For instance, we're defining user, address, we have some value, we call as JSON. What the compiler would do in this case? Well, out of the box, you will get a compilation error telling you that, sorry, my friend, there is no implementation for this type. Which kind of limits its usefulness, because then you would have to write all of these things yourself and provide them one way or the other, and it's kind of annoying, so why not just define those things like explicitly and call them explicitly and so on. But that's why Scala came up with this thing called type class derivation. And because this presentation is too boring, I will add some colorful slides that nobody would understand, but don't worry. The point of this slide is not as much about explaining all of this stuff, how it works. Basically, all I want for you to understand about type class derivation is that we are getting some type, decomposing it. Most of the time, it's about checking if it's either sealed trait or case class, and then trying to find if do we have some implementation for every single field of a case class, or do we have an implementation for every single subtype of a sealed trait? And then have some way of combining them together to get the implementation for your type. And if you are you are wondering, okay, about how the compiler know how to combine those smaller implementations into this bigger implementation, the answer is it has no idea. It has no idea. You are, as a library author, telling it how to combine the smaller things into those bigger things, and then that's where all those libraries like Shapeless, Magnolia, etc. come into place. So if someone did this, and we'll look at it, and we look at how like Circe does it from user's perspective, no implementator. Reminder: we have this trait, which has to be implemented for us to not by us, maybe by compiler, to turn some arbitrary type into the JSON. We have this extension method to make it slightly more easier to use. We have some types that we want to actually encode as JSON. And we want to have results basically like this. We have some value. If we run as JSON on it, we want to get something like this. If we have user and we run as JSON on it, we want to have something like this. Basically, we want to take every field name and turn it into an object key, and we want to take all value and encode it with the encoder for this value. So one way of achieving this is called automatic derivation. Basically, it boils down to the fact that we have some magical import, and as soon as this magical import is in scope, some way, magically, those implementations becomes available. Compiler is able to provide them for us. On the other hand, semi-automatic derivation, it works in a slightly different way. It works like, okay, if you want to have an encoder for address, we can build it for you, but you yourself have to put it into implicit scope. Then if you want to build an encoder for user, we can build it for you, but you have to put it into implicit scope. And so through semi-automatic derivation, you can use this method to put everything you need into this implicit scope, from which things could be fetched, so that you could just use it with those extension methods. A little bit more works, but for some reason, we'll see why people are doing this. So, how does things like this impact you? Well, let's discuss automatic derivation. We wanted to understand how this works and how this summoning of encoder address actually creates this instance. Basically, what compiler does is do something like, let's see if there is an existing encoder. Once it sees that, no, sorry, nobody defined that before. So as a fallback, because if it did, we could use it. But if nobody did, then as some sort of fallback mechanism, let's see if an case class is if an address is a case class. If it is, then we can see, okay, do we have implicit for the first field of this case class. Yes, good, let's keep on going. Then let's take a look if we have an encoder for another field, and so on. If it will be able to find encoders for every single field of this case class, it will combine them together and return this nice little, or not little, encoder for the whole thing. If it failed at any step, then compiler, well, it will fail. Semi-automatic derivation of address would be very, very similar with one difference. There would be no this step where we are checking, does it exist? If not, let's, as a fallback, generate the stuff. Which guarantees that every single time you are calling this semi-automatic method, it will return you a new value. And this is kind of important because usually when you have those derived encoders, you are doing something like implicit val, my new value, equals derived encoder. And if it would be able to fetch this value from the implicit scope, not as a fallback, but if it would always try to find this value and only as a fallback create a new value, you would have this issue that, well, all those implicit values would be calling themselves. So you would have circular dependency or on initialization, depending on if it's val or lazy var or def, you would have either stack overflow or null pointer exception, so not necessarily what you want. Which is why, basically, if you want to use semi-automatic derivation, it always has to return a new value because that's the only way to prevent you to get this circular initialization, errors on initialization due to circular dependencies. If we try to do this automatic and semi-automatic derivation on user, and reminder, user is having an address, things are getting a little bit more interesting because when we want to receive this encoder for user, then at first, of course, you will check, did someone define that? No. Then it has to check, is it a case class? Yes, okay. Is there an implicit for string because the first field of that case class was a string? Yes, okay, let's use it. Then, is there an encoder for address? And here where things are getting interesting because this stuff right here is basically repetition of this stuff right here. So automatic derivation out of the box is recursive. You're not only deriving the implementation for the top level thing, but for every nested stuff inside for which nobody provided the implementation, it will derive things in depth. Meanwhile, if you try to use semi-automatic derivation of user, the moment it gets to this address encoder, it only checks, did someone define it? If not, sorry, I'm failing. Which means that basically if you are using semi-automatic derivation and you are not importing automatic derivation to use them both at once, you have to define every single intermediate type if you have this deep nested hierarchy of case classes. And if you are wondering why I'm showing you this instead of code, then well, first example, we are focusing on the user side of the story, and we will see some user side examples later on. The code is in the repository, and there's a lot of this code. And also, if we wanted to dive deep into how all these Magnolia, Shapeless, and stuff work, all of that stuff works, we could probably spend next several hours here diving deeper and deeper in all of that stuff, and the outcome would be that everyone would be completely PTSD'd with all of that stuff, and we wouldn't even go to the part where, okay, but how does it affect me as a user? So forgive me for skipping all of the implementation stuff. I will only move on to how you as a user perceives those choices by the library developers. So why people bother with semi-automatic derivation? Because so far we only saw that there are those two flavors, but we haven't seen why people are using it. So the first reason is that people want to make sure that they have the same implementation everywhere. If you want to make sure that every single place in your application needs the same behavior, the same stuff, well, the easiest way to achieve it is by defining this thing only in one place and then calling that single place. It's basically the only way to guarantee by construction that you're using one implementation everywhere. And this is a use case that I'm not going to challenge because it's valid. The other reason why people are using semi-automatic derivation is speed. And by that I mean that there is a tremendous amount of anecdotal proof in the community if you speak to people that there were cases when they were using automatic derivation with CRC and then they have this one little nested hierarchy of JSON they had to encode and shove somewhere, and then they found out that this single file was compiling for 5 minutes, 10 minutes or more, that they have to manually tingle with those files and never understood what is actually happening under the hood, but suddenly the compilation went from 2 minutes to 10 minutes or even more. That their code was slowing down, that it was excruciatingly slow on the production. And then found out that it was all due to automatic derivation, and when they replaced this automatic derivation with semi-automatic derivation, suddenly it's all solved. No issue, easier to maintain coherence in your code, compilation times went down a lot, performance as well. But that was long, long ago, and people are still writing guidelines where they are telling you that you should always use semi-automatic derivation. Never use auto, it's banned in our code base, it's banned in our company. You should use semi-auto in some trait and then mix in your trait, and never, do this little import because this little import broke our CI, things like that. A lot of anecdotes and stories in the industry like that. So is it true? Well, we're getting to these examples when we are trying to testing those claims. So this will be a small CRC example. I will be doing this thing called round trip. So I will take some data, encode it as JSON, then decode as JSON back. And of course, this is something that you could do in unit tests to make sure that encoder and the decoder are matching implementation, so that if you send something in from one server to another, when the another server will be decoding stuff, it will get exactly the same thing as you send. You could also do this for the benchmarking reason, you can quite easily make sure that the code what you generated is fast enough. Serialization is one of those things that are bottlenecking our code when we are writing real-world applications. But for this particular test, I used this really, really nasty case class. But by that I mean that this outer class has some inner class, which has another inner class, which has another inner class, and some of those fields are repeated, and so on. And just by experience, I know that this kind of stuff will be really heavy on the compiler. So the semi-automatic version of this code is different by the fact that I had to manually add those 10 lines, deriving implementation of encoders and decoders for every single inner type before I get to the derivation of the outer type. So in theory, it shouldn't be hard on the compiler, because what I will be compiling is literally a single file. The definition of JSON is taken from CRC, so I'm not compiling that. The classes I'm using for testing are in another module, so they are not part of this test. How long it will take to compile that single file? So compilation of a single file, which is I don't know, 5 lines excluding imports, maybe 20 including imports on semi-automatic derivation. It shouldn't be tremendously slow, right? So on Scala 2.3, the cold JVM test, which under the hood is using shapeless, took something like 14 seconds. Semi-automatic version has 12 seconds. So single file taking more than a second is kind of surprising, I guess, at least for people who were not seeing these things before. Warm JVM is a little bit better. If you keep on clean, compile, clean, compile, clean, compile, afterward Scala compilers warms up a bit, but even then it's like 4 seconds against 3 seconds. Much better, but still people could be surprised why it takes so long. Surprising stuff are happening on Scala 3 because there the automatic derivation of for this single file took me 46 seconds on cold JVM and 16 seconds on warm JVM. There you can really see that semi-automatic derivation takes much less because it's 10 seconds against 1 second. So you could really see why people were choosing semi-automatic derivation. Well, kinda, because we are still like wondering why the difference is so small on Scala 2.13 and so huge on Scala 3. Before we try to guess why, we can also look at the performance. Like, we are generating code, so supposedly the performance should be the same, right? Whether we use automatic or semi-automatic derivation. And sorry for just copy-pasting stuff from the Java benchmark harness as opposed to making nice little graphics, but if we look at Scala 2.13, we can see some difference, not big, but there is some small difference that that we could, probably for some people it would be negligible, for some people it wouldn't, but those compile times, they're really close. However, on Scala 3, we can see that there is an order of magnitude difference whether we are using automatic or semi-automatic derivation. Like, if you are using CRC and you derive codecs automatically, then for those pathological cases, at least those that I produced, you could get 10 times worse performance. So probably something that people pay attention to if they are worried about all this stuff, if they are using stuff in production. So how we could explain those results? If someone follows the history of Scala 2 development and reads all those nice little PRs, they could see that the author of Shapeless, Miles Sabin, were doing some attempts to optimize the compilation times. So he made one PR, which was closed, then another PR, which was also closed. Finally, yet another attempt was successful and it got merged. Then he made another optimization which was merged, and so on and so on. And in one of those PRs he was boasting that the size of that when he was comparing how long it took for something to compile in seconds, depending on the size of the, let's say, a case class. Then you could see that before the optimization, it was really bad. Why after the optimization, it's, basically it's an order of magnitude better. So it's much better. And when you read those messages in those PRs, you can see that they tried to have those things merged in Scala 2.12, but they didn't get it in time. So they decided to do this in Scala 2.13, and the attempts to backport it in 2.12, I think they failed or were scrapped. So people who have experience with automatic and semi-automatic derivation before 2.13 still remembers times before those optimizations took place, and you could see that the difference could be much, much prominent than today. On the other hand, when it comes to Scala 3, you could see that those PRs from Scala 2.13 were ported to Scala 3, but apparently there are differences between how shapeless works and how mirrors are working in Scala 3, so those optimizations don't matter as much. Some new optimizations have to be made in Scala 3 to, you know, make that gap smaller. But were there any other attempts to improve performance, other than semi-automatic derivation, obviously? One such attempt was Magnolia. This library was written as an alternative to shapeless, or nowadays also mirrors, but at the time only to shapeless. And it's boasts about better API. So if you want to start doing this type class derivation business, it supposedly have better API than shapeless or mirrors or whatever. One of the reasons why many people are using this. It also boasted better performance, better compilation times, and better error messages when the derivation fails. So let's start with the last claim. We have this nested hierarchy of classes, user which is having address, and address is having a street, and on purpose decided to encode the name of inside the address as something that seriously, cannot work with out of the box, because I'm using nothing and either, things like that. Just to make sure that this derivation would fail and see what kind of errors would be produced. And we were starting with semi-automatic derivation. So I have several implementations of this. 2 of them are provided by CSC itself. Magnolia, I had to encode myself. So shapeless, if we fail in this nested field, well, it would still help us, telling us that, sorry, we could not derive it, because we are using semi-automatic derivation and we are implementing all of these intermediate types ourselves. Then, well, we know where the derivation failed because the compiler is pointing us to the actual line in the code. And that's the only help we're getting. Mirror in Scala 3, well, they're able to tell us, sorry, we failed to find an instance for this specific type. So it's a little bit more useful, not that it failed, but it failed because of this. And in case of Magnolia, we're seeing something like, inside the class of this name, in this field, we were not able to handle it because there is no implicit for this field. So quite a detailed message. Probably even beginner would be able to figure out at least what to ask around when they try to fix this kind of error. But this is the semi-automatic derivation. If we are talking about automatic derivation and we are failing this field in deep nested in the hierarchy, you always get only could not find implicit value. So if you are using automatic derivation, all those 3 libraries are equally bad for telling you how to fix this nested stuff. Sorry. So what about the compilation times? A reminder, we are doing this round trip when we are generating decoder and encoder. So on Scala 2.13 nowadays, there isn't that much difference when it comes to compilation. You could see that automatic derivation is slightly faster, but not much. Automatic derivation almost as fast as shapeless, probably thanks to all those improvements by Malice Sabin. Before Scala 2.13, probably the difference would be much, much bigger. Interesting stuff is happening again in Scala 3 because Magnolia, instead of helping stuff, it's making stuff worse. We could see that using Magnolia instead of mirrors on Scala 3 increases the compilation times so that in some cases, at least for my examples on my computer, I had to wait for the result for over a minute. After a warm-up, the results are better, but still worse than with just simple mirrors. And that's because on Scala 3, Magnolia is implemented on top of mirrors, so whatever overhead you have when it comes to compiling mirrors, Magnolia just adds something extra on top of it. In Scala 2, Magnolia was implemented with macros, so it was not using any of the stuff that Shapeless is providing, so it could improve some things, and probably that's why many people were starting using Magnolia in Scala 2.12. But how does it translate to the runtime? So when we look at the benchmarks, we can see that Magnolia is slightly better on Scala 2.13 than Shapeless. Again, maybe there were some optimizations which made the difference smaller in Scala 2.13 than before, but if you are using like a recent version of those Scala 2.13, well, the code that it generates it's not a deal breaker if you use Shapeless as opposed to Magnolia. On Scala 3, well, we can see that semi-automatic derivation with Magnolia gives you better results, like 25% in this case, than mirrors. So you could see that there is some optimization when it comes to semi-automatic derivation in Magnolia. But if you are using automatic derivation, you can see that it is an order of magnitude slower than the generic auto. I have some suspicions that it's related to having those really, really big inlines that JVM seems that, okay, the method that you are generating is too big to optimize, so I'm giving up. So, interesting things are happening on Scala 3. So if you ask me, like, those approaches, well, they differ when it comes to implementing the library, but for you as a user, there isn't much difference. A little bit better messages if you have semi-automatic derivations, but more or less the same results for you as a user. Sometimes catastrophic compile times when you're not expecting it, but other than that, like no difference. So, since we are talking about JSON, we are using JSON libraries as an example, so JSON Scala is a library that does things slightly different than CRC. Performance is a priority for them. So every single design decision that this library is making is about performance. And it first no automatic derivation, because when you have automatic derivation, you are creating instances of your interface for all those intermediate types. All those instances obviously have to allocate some memory, and memory allocation is very expensive, so let's try to avoid it if possible. So it also like not using any sort of intermediate instances. But you might ask how it avoids that, because if we are using Shapeless or Magnolia, all of stuff, and we get used to read type class as type level as now to Shapeless or whatever it was called, you got used to this idea that we have those small implementations and we are always combining them together, and all of those implementations have to exist as a separate instance of this trait. So how does JSON approach this differently? If we look at the code, we see that we only have to create one instance. But this one instance is handling things recursively inside. When it will see that, okay, I need to handle this out type. Okay, so let's then see what field it has. Let's generate the implementation for it. Oh, it has another case class, so let's inside the same macro generate implementation for that. Then it says that it's had another nested class, another nested class. All of that stuff is happening inside the same single macro. without relying on fetching implicit from the outside. Implicits are only used to override the behavior, to provide your own, providing your own codecs if you want to somehow modify the behavior in whatever way possible. The API is slightly different than CRC. It has either throwable as opposed to this AST from CRC, but basically conceptually it's very similar. Other than the fact that you have to provide this single implicit, but this implicit is handling things recursively with all the nestings. If we try to draw how to CRC handle stuff, we can see that this diagram looks a bit more complex, and it looks a little bit more complex because if we like stop reading the things and just zoomed out, we could see that CRC and all of those libraries with the same approach as CRC tries to delegate everything on the compiler and implicit search. If you have any sort of branching, do this, otherwise do that, otherwise do that. It's dumped on the compiler and the typer and the type checker. In JSON-eater, because it has macros, those things exist as an if-else's written explicitly by the author inside the library. When we want to provide some built-ins in CRC and all those libraries that are working like CRC, we have to provide those instances explicitly, and they have to be somewhere in the implicit scope. For JSON-eater, those things are encoded somewhere in the macro. It just is, you have this type, okay, I have this special place in my code which tells me how to handle that stuff. So it's a bit harder on the author, but perhaps it's better for the user. So let's see if it is. Is all that like gibberish talking about JSON-eater worth anything? So, as you can see, JSON-eater is working slightly better than semi-automatic derivation when you look at the both cold and hot JVM compile times. I'm not sure why there's this bump for JVM on Scala 2.13, but when I was rerunning the code a few times, it was consistent, so I guess it is what it is. But we can see that it consistently is better on Scala 3. It's faster than both Magnolia and Mirrors when it comes to compilation. And as a reminder, this code has one implicit as opposed to 10. So I believe it's much more user-friendly if you get better compilation times while writing less code and without macro optimizations. So what about the runtime performance? Perhaps it's a trade-off. We have better compilation times, but the runtime is trash. Well, it's 3 times as fast. So not only you are getting better compilation times, you are also getting better performance. At this point, I have to admit a little bit that I am slightly cheating because CRC is converting case classes into this JSON representation, and when it parses, it also like takes this JSON representation and turns it into a case classes and seal traits. And JSON-eater Scala is handling strings or input streams. So if you were using if you were writing the normal code when you are taking a string, decoding it into as JSON, and then decoding this JSON as this actual type that you want, this difference would be even bigger. So I'm kind of cheating, but I am giving basically CRC a head start, and it's still failing. But we can ask, okay, can it be automatic? Because we still have to write that single implicit, and it might be annoying sometimes. So this is a problem that I had in my own library in Chimney. And again, I am not going to show you chimney. I'm only going to show you that we have similar problem. We wanted to have the derivation that should be recursive. We wanted it to only use implicit to override the behavior provided by the library, whether that existing behavior is doing something out of the box or failing. Sometimes we don't want to replace failing with support for your own types. But as opposed to JSON, we wanted to support automatic derivation without breaking those two rules above. So long story short, we came up with this weird pattern that basically we split the type class into two things. One of them is intended to be used by the user or by semi-automatic derivation, and then we have this dedicated auto-derived type, which is always returned by automatic derivation, but which is invisible to the macro when it looks for implicits. It has this slight little downside that we have to use the wider type when we are using extension methods. And in macro, we have to be careful to only use this more specific type and never the wider type, because there is this, subtyping relationships, and you can all study all of that stuff in your free time, because you are not really interested in this. You are only interested if it can be used outside of chimney. And the answer is yes. I spent some time to write a wrapper around JSON eater, only Scala free, because it was easier. And with this wrapper, I only need to do this one import, call all those methods provided by, also by my wrapper. And it would also use that recursive approach with only using implicit to override stuff. And it looks, if you look at it, it looks very, very similar to CRC with automatic derivation. But if we compare it to CRC with automatic derivation or semi-automatic derivation, it's only on Scala 3, so look only at the right side on the blue bar. We can see that there is small overhead over row JSON eater, because I basically wrote a wrapper around it, but it compiles around the same time. So we have something which is much more convenient than CRC's semi-automatic derivation, compiling fast, something much more convenient by CRC's semi-automatic derivation, basically as convenient as CRC's automatic derivation, but compiling faster than its semi-automatic derivation. So, sounds really good. If we look at the benchmarks, we can see that the overhead is visually unseen, at least by me. So, also no drawbacks. But of course, you can have some dubs like, okay, JSON eater was built for performance, CRC was built for like other stuff. And it isn't like, fair comparison, considering that those libraries might have different philosophies, and it's like apples to oranges. You cannot even guarantee that those differences are specifically to the differences in derivation. It might be different in something else. And this is a fair critique, which is why I decided to do a more fair comparison. So I basically wrote my own type class. If you were using CRC, you probably saw something called show. This is like the simplest example of how to do typeless derivation. It's basically CRC's way of doing a better toString. Except there are some extensions to it called showPretty, which is like toString, but with those nice indentations for nested case classes, nested fields, and stuff. So I decided to do exactly the same thing, except instead of concatenating strings, because I didn't want to, I decided maybe I would improve things a little bit if I was just using string builder and appending to the string builder rather than concatenating strings. Maybe it would be cheaper, at least it would be funnier for me. So you can see that I had this sort of like type class, it should have this API, and it should print things like that for the code I'm showing in the middle. And once I had this API and once was having some code to print, I decided to implement it as automatic and semi-automatic derivation with shapeless on Scala 2, then implement it as automatic and semi-automatic derivation with mirrors on Scala 3, then automatic and semi-automatic derivation with Magnolia on Scala 2 and 3, and finally with what I call sanely-automatic derivation using macros. And I helped myself using Chimney microcommons because some of the stuff that I'm using inside Chimney I extracted as a separate macro utility. And with that I implemented this stuff for Scala 2 and Scala 3. So I believe that should be quite fair comparison. And well, my first approach looks like this. Sanely automatic derivation is at the end, so well, not great nor terrible. Like, at least it's better than automatic derivation with shapeless, I guess, or with mirrors, surely, but still slightly worse than Magnolia or semi-automatic derivation with shapeless or mirrors. Benchmarks, well, with benchmarks, it's also nice, but you could also argue that Magnolia works better or that semi-automatic derivation works better, so someone could think that, hey, sorry guy, your experiment kind of failed. But then I remember that JSON Eater had this one more trick, that when it reuse some stuff inside this code, it basically creates, like, inside this generated code its own defs, which you use to kind of cache whatever it already derived, so that when it see the same time another use in the same macro twice and thrice or more, it just defer to this def so that it would not have to derive it again, inline it again, just reuse stuff reuse the work it already did. And it was well, not necessarily a simple change. Initial work was requiring me to do some new utilities, but I extracted it to Chimney microcommons, so right now it's a simple change, something that you could implement with a, let's say, a single PR, very non-invasive PR. So you can ask, okay, it's non-invasive PR, so would it make a difference? Well, it does, because right now this code is compiling the fastest of all of them on every platform, irrelevant if it's cold JVM or hot JVM. And it's also working faster on every single platform. Irrelevant, so it's it's benchmarked, so they are already warmed up. But yeah, this sanely approach now works better than shapeless or Magnolia or mirrors, Scala 2, Scala 3, automatic, semi-automatic. So for something that requires you only to have one import and then it works, better than something which requires you import and several things manually. It sounds kind of nice. And also, as a bonus stuff, debugging is better, because if we are doing everything inside a single macro, and if we decided we want to fail in this nested field deep down in the hierarchy, we are able to show in this macro message that which type was the cause of the failure. If I spend a bit more time in this project, I could tune this error message even more. I could say that this thing happened in this field of this class. I could show how much the derivation took. Obviously, I can also aggregate the failures if there would be several things which are failing inside the macro. I could show all of them at once, as opposed to making you fix one thing, then compile, make it fail again, then fix another thing. You could fix all those stuff in a single step before recompiling stuff. So that's a huge help. And also because macros allow us to. And here I use this nice thing called X macro settings, which is something which allows you to provide settings to the macros, which hardly any macro library uses, but there is a possibility, and people should start using it more. So with this thing, I told my macros, okay, be so nice and log your logic. And then I could have this nice, real structural log telling me what the macro did. Okay, so now it's trying to use implicit. Now it's looking if we already made some def inside, which is using this. Then try to use built-ins, case classes, sealed traits, and so on, with those nestings for every single field. So you can, fine-tune this kind of logs to your heart's contents to make things as easy to debug for you and your users. And also nice stuff, you don't have to use print lines for that, because macros have this thing like reporting and info errors, which means that if you would enable that stuff in Scala C macro options and run this inside Visual Studio Code, you would see that the dashed line showing you that there is some info, and once you would hover your mouse over it, you could see all of that log inside your IDE without having to look at the output of your build tool. So it's really, really convenient, and I believe people should start using it more, because one of the things that you could provide with this kind of logging would be like, the final expression. So if you wanted to see, okay, but actually what is the expression that this macro is generating? Well, you could just, enable that one little thing in your build tool, hover, scroll, and see, oh, this is what it generates. And that's really, really good when it comes to debugging stuff and figuring out what your macro is doing. So that's all that I had to prepare for today, so I might go to the summary. Yes. So last year there was this Virtus Lab Scala survey, which was questioning, okay, what are those things that are making your life miserable, what we could do to help you fix stuff, make your life better, make you more productive. And 53% of developers were complaining about the compilation times. And I'm not telling it's always typeless derivation, but a lot of that is typeless derivation. And the fact that all those libraries out there, almost all of those libraries out there, are picking the way of providing typeless derivation, which is not compiler friendly. So perhaps we could start giving the library developers feedback that they might be able to do something about it, that they might improve the compilation time, perhaps even improve the performance in the runtime, surely improve the error messages, because implicit not found, sorry, it's 2024. We could do something about it. And perhaps then we would have less people complaining that Scala is hard, that Scala is impractical, is academic, and so on, because we can really make this typeless derivation that a lot of people rely on in their jobs easier. It's just a matter of applying the right utilities. I'm not going to say that all these libraries like Shapeless, Magnolia, Mirrors, CompileOps are wrong, bad, etc. Because if you look at the code I had to write to implement those benchmarks, you could see that usually it was something like, I don't know, 15 lines of Shapeless against 500 lines of macros. So you could see that if people had to start with macros, they would just give up, and we wouldn't have CRC, we wouldn't have pure config, we wouldn't have all those variety of libraries that we have out there. But if we want to have production-grade libraries, if we want to have libraries which are friendly to users, friendly to developers, which we could recommend people to start using this stuff, it's better than on Java, then unfortunately we have to give feedbacks to the developers that at some point they might need to move away from those stuff. that perhaps those libraries are really good for prototyping, for fast iterations, but they are prioritizing the library maintainer's experience over library user's experience. And if we want for Scala to not die in the next 5 years, perhaps this is something we need to think about and do something about it. And also, if someone is hoping that, you know that maybe in 5 years the Scala compiler team makes some super optimization and all of those problems disappear, this improvement is something I could do in a week with my own library. And all of those improvements that Miles Sabin was doing to Scala 2.13 took him several years. And I could still beat him with a single PR in my code without waiting for Scala devs to fix compiler, because it's super complex machine. So I'm afraid the only way for us to improve our experience is if we took things in our hands and start fixing our code without waiting for the compiler team to try to fix our code in their code. And with that saying, I also want to tell you that, okay, I don't want to force my approach on the code on you. I only wanted to, I don't care if any of you would ever use my sanely-automatic derivation, if anyone of you likes it. But if that would inspire any of you to give some feedback to the library developers, and if you are a library developer, to start challenging some assumptions that our community was living over the next several years, that this is the only way for building libraries. And if you find your own way, and this way will make Scala better, then I will be happy. And with that said, thank you.
Many thanks for the talk. That's impressive. If I understand you well, currently it's only available in Chimney commonly?
Yes, while working on migration to Scala 3, I had to, because the Chimney is a very, very complex library, I didn't want to have two code bases to maintain, which are only held together by unit tests. We decided that as much as possible of the business logic should be shared. So I developed a way of sharing the logic between macros on Scala 2 and 3, and part of that was also sharing a logic of utilities for parsing things like case classes and anivals and seal traits and stuff. And because I didn't want it to live in the same module as Chimney to pollute stuff, it ended up as a separate library called Chimney Macro Commons. So it exists for a year, maybe a year and a half, something like that. I have to warn you that there is no tutorial or no documentations about this library. The only documentation is Chimney and maybe the examples you could see in this repository, because I'm using it here. But yes.
Thank you. If at some point some other library developers want to use it, if it's useful for them at some point, what I understood is for them, the cost would be to have much more plain code to write for it to profit from fast automatic derivation. Is that it?
Yeah, like if you want to write macros, unfortunately you have to prepare for that. You will have much more code to maintain. I believe that if there was some library, for now I only know one, which would help in this task, it would be great. You could still have this overhead of maintaining macros, and they will always be much more, they will have always much more overhead, for at least when you are starting, than writing things with just implicits. But the more and more complex your logic gets, at some point when you have those inline devs with those stuff fetching things, like writing code with simple if-elses start getting easier, even with all those overhead of maintaining macros. But it's definitely not something I would recommend anyone to start with. If you want to have a typeless derivation library, start with all the stuff like shapeless, implicit macros, because they're much better to learn, to get some feedback, to understand how it works. Only when you are no longer your main user, no longer the person who, okay, I'm missing something, so well, I will add this to this library. Some other people, well, there are none, so I don't have to care. Once you grow out of this, once you start sharing the library with other people, once they start relying on your library and they would need it to work, they would need it to work fast, be easier to debug and so on, then you might decide that perhaps implicit-based approach is not very good, because it's also very, very hard to keep things binary compatible, as you can see with Circe, which is breaking things with every other release, at least if you are using those, typeless derivation and stuff. So yeah.
By the time I walk to the next question, quick update on the community party. It will start at 6:30 on the hour.
In the case of the automatic derivation, if you have to read the implicit twice, will Scala be able to cache the result of the first derivation, or will it derivate that twice each time?
Basically, you should assume that every single time you're using automatic derivation, it's not cached, but one of the reasons why the semi-automatic derivation and automatic derivation started getting similar results on Scala 2.13 was that the compiler team, MySabin, basically implement this kind of caching. But this caching, you should also assume that when it works within the scope of a, let's say, single file. So if you are deriving the same stuff in several places, you should probably assume that it's going to be derived several times over. However, if you have this, sanely approach to automatic derivation, the cost might be much smaller. So before it bites you, it will take a lot more time. You would have to use those things in a lot more places at once before, it will bite you as much as it bites you right now with the current approach.
In your benchmark numbers, I expected to see some radically different compile times, but I was surprised to see the runtime performance sometimes also vary by a factor of tens of times. Do you have any insight into? I would have assumed that sort of once the compile finished, that the resulting byte code was more or less the same. Do you have any insight into where that extra time is coming on the ones that have slow runtime numbers?
I didn't do very deep investigation, but I have some educated guess, because in one of the reasons, if you look at the code, you see that the nesting of these classes is like 5 levels depth. And initially I started with 10 level depth, but then quite often I had issues like, I'm sorry, but your code excluded the maximal size for the method on JVM. Or sorry, but your code is you have Stack Overflow the compiler or things like that. So the 5 was the border number on which I could still compare those libraries without these approaches, without one of them being basically unusable because the compiler would give up. And in some versions, when I was testing macros, I saw that if you are naively inlining stuff, you could easily exceed maximal size of the methods on JVM. So I had to use a trick to put things into defs, so that because def, then it would be smaller chunks in the bytecode and things would work. And after I used this approach with explicitly using def with caching, for caching this second approach to macros, then it was no longer necessary because that was handling it. But my intuition, again, I haven't validated it, but my intuition is that when you're using inline def with mirrors, it naively inlines everything in the same method. And because it's exploding the size of the method, you might think, okay, inlining is good, but the JVM has some limit on how much bytecode it tries to compile into, optimized code, and at which point it said, okay, this method is too big, I'm giving up, I'm only going to interpret this. And my guess is that like Mirrors and Magnolia with this automatic derivation inlining everything with no, respect for whatever, generating so huge methods that the JVM says that, sorry, I'm not gonna optimize that. I'm not gonna run C2 compiler. I'm only gonna interpret that, and then you get this huge hit in the performance. But that's not just educated guess. I didn't do any sort of investigation. This is just my intuition.
Any other question? Thank you very much.